Hello and welcome to the second part on statistics in chemical measurements, where we'll be looking at things like method validation, how to remove outliers from our data sets, as well as trying to work with some more complicated analyses and things like environmental samples. So without further ado, let's get started. So last time in part one, we discussed things like normal distributions, this idea that measurements, our analytical measurements or instrumental measurements are all usually distributed around a mean value. And they're pretty evenly distributed on either side of the mean, with the areas under that curve being equal to the probability of finding a point at that particular region. The F-test was used to help us to look at how different data sets were related to each other by comparing their standard deviations. Confidence intervals would help us to determine the location, if not the exact value for the true mean. And the t-test would help us to determine origins of errors and whether or not the errors were originating from random errors or systematic errors. So today in this part, we will be looking at the Grubb's test for an outlier. So this is how we would determine whether or not we should remove a data point from our data set. We'll also talk about noise in instrumental measurements. We'll look a little bit at method validation. And then finally, we'll finish off with dealing with some complicated samples. So things like real world samples, such as river water samples or checking for pollution near chemical plants in groundwater and things like that. So first, the Grubb's test. So this is where we check our data and we try to remove any outliers. So the Grubb's test helps us to decide if a questionable datum outlier should be discarded. So take, for example, this mass loss data set. So in this data set, we have 7 samples. Each one of them are, well, 6 of them are quite close together. So they range from about 10.5 all the way through to 11.3, which is a spread of about 0.8. However, there is one data point amongst this data set, which has a considerable deviation from this kind of range. It's 8.4. It's considerably lower than the next lowest data point, 10.5, about 2.1% away from that value. So we ask ourselves, should the value 8.4% be removed? Now, we could probably say, sure, we could remove it, but is it statistically reasonable to remove our data? And so the Grubb's test has been tested many times and has been shown to be a reliable method for removing data points which are outliers, which provide no meaningful loss of statistical relevance to the data set if they are removed. And so in order to complete a Grubb's test, we have to calculate a G value for our value that we want to remove. And then we have to compare that to a table of G values at certain confidence levels. A table for a 95% confidence level G values is found here, where we have observations, i.e. the number of data points. And we have here the G table value for that. So we would calculate our G value for our data point as such, where it is value minus the mean of the sample divided by the standard deviation of that same sample. So the G calc is equal to, in this case, 8.4% minus 10.53%, which is the average of this data. And then that's going to be divided by 0.901, which is the standard deviation of this data set. And so that's going to be equal to 2.36. Now we look up the G table for this 7 data point set. So the number of observations here is 7. So this is different from the t-test or the f-test, where we were looking at degrees of freedom. In the Grubb's test, we're simply looking to see how many data points there are, or in this case, in Grubb's nomenclature, the number of observations. So the number of observations in our data set is 7. So the G value for that would be 1.938. Now we compare that value to our calculated value, and we see that the G calc is greater than the G table. And so this tells us that the point should be removed. Had G table have been equal to or greater than G calc, then we should keep the calculated, or sorry, the outlying data point that we were considering removing. So we'll move on then to method validation. And within that, we'll look at also noise in our data, because that's an important consideration in many of the methods of validating our method. So specificity is one thing we look at. That's the idea that an instrumental method will be particularly relevant for our analyte. Linearity is the idea that for example, our calibration curve should be linear, so it should have a proportional response to the concentration increases or decreases. Accuracy, then, how good is our data at approaching the true mean? Then the precision, which is our ability to reproduce the data, even if it is not accurate. The range, then, within which we can make measurements, and then the limits of detection and quantitation, which are related to this range. So the first thing we wanted to talk about is signal to noise ratio in our measurements. So here we have a peak, and surrounding that peak is some noise. Now, this noise is caused by various factors and usually comes about in instrumental analysis because of thermodynamic changes, expansion or contraction of detectors or circuitry, or just the casing indeed of the instrument itself. It can also come about due to quantum effects. It can be caused by vibrations in the room or the building. There are a great many different things which can cause the noise, and there's no real way to completely eliminate it. Even with significant amounts of dampening, we can only get down to a very minimal level. There will always be some amount of fluctuation. So whenever we're calculating the signal to noise ratio, it is calculated as 2h over h, where h is the sort of the range of the standard deviation of the noise measured at various points. And then big H, is going to be the height of our peak measured from sort of the average value of the noise here, this middle line. So to determine signal to noise ratio, the best way is to zoom in on a peak with baseline clearly visible on either side, and then measure the peak height, measure the noise level, which can be hard due to the random nature, such as thermodynamics and quantum effects, which I just spoke about a moment ago. And then we should pick several areas around the peak and measure their noise levels and average, which will give us this small h value. And so the signal to noise ratio calculation can be done like this. Signal to noise is 2h over h. Blank solutions are very important during our method validation, and we will talk about them a lot. So it's a good idea to introduce them now. So blank solutions are prepared from the same reagents and solvents used to prepare our standards and unknowns, but without the analyte. So in every way, they should be identical to our measured samples, our standards, which we'll use for calibration curves, and our unknowns, which are the things that we want to analyze and know the quantity or concentration of. But these blank solutions should not have that analyte of interest. Then the blank tells us the response of the procedure to impurities or to interfering species in the reagents. So our solvent may cause an instrument response. There may be other impurities present in our solutions which produce responses in the instrument which may complicate or interfere with our analyte. And so this blank will tell us to what degree that is present in our solution. And so whenever we are making any preparations for a calibration curve or an unknown measurement, the response of the blank, i.e. the instrument response, the absorbance, for example, of the blank must always be subtracted from any other measurement. So no matter what we do with our analytical measurements, we must always measure a blank sample. So one of the ways in which we utilize these blanks, we utilize methods, is to determine concentration. That's already been established. But one of the ways that we determine our concentrations is through development of a calibration curve. This calibration curve is formed based on a line drawn through several points. And that line is determined using the method of least squares or linear regression. So we get a best fit line straight through our data points, and hopefully our data points show a linear response. That means that as analyte concentration either increases or decreases, the peak height changes in a proportional manner. So it is going to be proportional to the analyte concentration. So the equation of this line is y is equal to mx plus c, where m is the gradient of the line and c is going to be our y-intercept. So manual calculation can be time consuming, and so a spreadsheet can be used to simplify this process. You can find the equations for the method of least squares in other videos or online or in your textbook even, and that will show you how to manually calculate these things. But ultimately, the spreadsheets that are commonly available are going to be sufficient to calculate these linear regression fits. So our calibration curve, as I've said, is dependent on the idea that there will be a proportional response from the instrument to changes in concentration. However, there are going to be certain ranges over which the response is going to be linear, and then there are going to be other ranges where the response is measurable, but because the response is not proportional in the same manner to the concentration as it was before, we will not be able to use it in our measurements. So calibration curves, as I've said, show response versus the amount of analyte and are produced by measuring samples with known quantities of a sample. So this means, like in the previous example, we made solutions with 1 ppm, 2 ppm, 3 ppm, 4 ppm, and so on. That's parts per million. We learned about that in a previous part of this course. Now, a corrected linear response is going to be proportional to the analyte quantity. What does it mean by corrected linear response? Well, this is the response of the instrument, so the measured value for example, maybe the absorbance that was measured, and then this is going to be corrected using the absorbance of the blank. So it will be the signal of the instrument measured for our analyte minus the signal from the blank, and that will give us our corrected linear response. And so this can be corrected by subtracting the signal of the blank. Now, the linear range is when the response is proportional to the concentration. And so you can see it here in blue. And then this blue dashed line is what would happen if the response was always linear to the concentration. However, it's not always linear to the concentration. And sometimes we end up with deviations from that at certain high concentrations. So as concentration increases above a certain limit, the limit of linearity, as we'll learn later, this line here, then we will reach a dynamic range. So this is still, as I've said, measurable to the instrument. However, this measurement is now complicated because of various factors, but usually the one that's the biggest factor is that the analyte is now interacting with itself. Previously, you see whenever it's in low concentration, the analyte molecules or atoms or whatever they happen to be are sufficiently far away from each other, sufficiently separated that they don't actually interact with each other. But as the concentration increases, it increases the chance that the analyte will come in contact with other analyte molecules. And this can cause changes in the instrument response, because there are new pathways of relaxation. A lot of these measurements rely on the idea that something is going to be absorbed or some energy transfer is going to happen to our sample. So whenever the analyte can interact with each other, they can cause new pathways for relaxation. So the dynamic range is when there is a measurable response to analyte, though not all amounts may produce a linear response. So the dynamic range includes the linear range, but it also includes the area outside of the linear range where we no longer have a linearly responsive instrument to concentration. So the dynamic range then is at the detection limit, the analyte is present due to the small amount, and accurate quantitation is not possible. So this is the detection limit. So this is the idea that this is the minimum amount that is allowed so that we can actually measure it, and we're sure that it's not actually just the noise. So we can see here how it's related to the noise. The noise is this black line, and so, or the blank line. So this is effectively the noise of the measurement. And so the limit of detection is typically defined as 3 times the standard deviation of the blank. So it should be 3 times the standard deviation of the blank, and that will give us our limit of detection. But the limit of detection is not the minimum concentration that we can use for the development of our calibration curves. That is something different. That is called the limit of quantitation. The limit of quantitation is 10 times the standard deviation of the blank. So the dynamic range is the limit of linearity over the ratio of the limit of linearity to the limit of quantitation. So it ranges usually from about 2 orders of magnitude to more than 6 orders of magnitude. So that's kind of going from tens to hundreds to thousands, and this is going all the way up to millions. So the limit of quantitation is 10 times the standard deviation of the blank, where K is usually, K being the number of times the standard deviation, is 10 times that of blank. So you can see here 10 standard deviation of the blank. This is 3 times the standard deviation of the blank is the limit of detection. So you can reliably say at the limit of detection that we have the analyte present, but we cannot say with accuracy that the concentration of that sample. And then the limit of linearity is when the signal is no longer proportional to the concentration. So that's whenever it starts to get curved, it's no longer a straight line. And that happens at high concentration. So selectivity. So this is important because oftentimes, especially whenever we're measuring real world samples, there is going to be a certain degree of interference in our samples. So no analytical method is completely free from interference, and the best method is more sensitive to the analyte than the interfering species. So the more sensitive a method is to the analyte, it means that the effect of any interfering species can be minimized. So say we have here two independent signals, but if we mix them together in the same sample, we would end up with overlapping peaks. You can see here the blue line and the red line, they kind of overlap with each other. So say we wanted one versus the other, we would need a method which would maximize the response for, say, the red line and minimize the response for the blue line. And that would be a selective method for the red line. Now, if we have a matrix of both A and B, so that's A is red and B is the blue line, then our signal is going to be a mixture of both A and B. Plus the signal of the blank. So this is the gradient of the calibration curve of A, which is here, plus or times the concentration of A plus the gradient of B, which could be the blue line up here, times the concentration of B plus the signal of the blank. Remember, the blank is always present and always needs to be subtracted from the signal that we measure. So the selectivity coefficient then, so how selective a method is to either the signal from B or A, is given as the ratio of the gradient of B to A. Say we wanted the selectivity in terms of A over B, then it would be M over A, or MA over MB. But in this case, we're looking to know how much more selective is our method for B versus A. So Ks vary between 0, no selectivity, and large numbers, which are very selective. 0 would indicate to us that the method doesn't really detect B at all and is very selective and very sensitive at measuring A. So the limit of linear response happens because of saturation. So the detector gets saturated, so it means it can no longer actually really measure the sample. So the limit of linear response, so the point of saturation for an instrument detector so that higher amounts of analyte do not produce a linear response in signal. So what happens is the detector kind of gets overwhelmed. If you imagine you're lying in bed asleep and the next thing is the curtains suddenly open on a bright sunny day and you open your eyes and there's that initial sort of aversion to the light and you want to turn away. It's kind of what happens to the detector. It gets overwhelmed by the amount of light that's suddenly incident on it and it just turns away, albeit in a quantum and chemical manner. But here we can see what would be similar to a chromatogram from maybe an HPLC. So you can see here the lines end. Usually we, of course, think of our lines as being continuous. They never have any gaps. They just keep getting drawn like this. But in the case of when the linear response has been reached, we end up going off the scale of the system and we reach some point where the detector is saturated. Usually this happens for things like solvent. Usually, especially in HPLC or GCMS, we're not super, or just GC, we're not super concerned about the solvent overwhelming the detector since we're not really interested in knowing the concentration of our solvent. What we're interested in is knowing the concentration of our analyte. And so peaks like 1 and 2 would be perfectly fine. You can see that they have well-developed peaks. So another idea of method validation is the linearity. So this is whenever we generate our calibration curve and we ask ourselves, how well does this calibration curve follow a straight line? And so one of the ways in which we can determine this is by using our R squared. So this is going to be the square of the correlation coefficient. So R squared is given here, where it's going to be the sum of the difference between the X point and the mean of X's and the Y point and the mean of the Y points squared over the individual X's and Y's individually squared. And so this R squared value, the closer it is to 1, the more linear the data. And so we want this to be very close to 1 whenever we are producing our calibration curves, because this indicates that we have a very good linear response to the data and the concentrations. So you can see a few different examples. We have here an R squared value of 1 because the data points are indistinguishable from the line. We have another high R squared value of 0.991. And in this case, you can see that the linearity is still pretty good. But now you can see some of the data points around the line. And then we can see as we increasingly have more dispersed data, here, the third and fourth are both pretty linear, not great. I wouldn't really want to use those as calibration curves, but in a pinch, they would suffice. Whereas the last two here are just nonsense. This is not a reasonable place to be using linear regression to be forming a calibration curve. You would really need to question your instrument or your analytical chemist in this instance, or your skills. Like you would need to go and prepare the samples again. And this last one is just nonsense. This is random data. It is not in any way showing any linear correlation. You can draw a line through it, but you can see from the R squared value, it's so low that there is effectively no correlation or no linear correlation here. So the first two, good. Third and fourth, not so good, but I guess okay. They do show some degree of linear proportional response, but the fifth and sixth are just not acceptable. So going back to the different regions of our calibration curve or our instrument response versus concentration, we're looking at useful ranges of an analytical method. So as I've said before, the dynamic range is what can be measured across from the limit of quantitation all the way past the limit of linearity until we reach sort of detector saturation limits. So this part here between these dashed lines indicate the linear range inside which the measurement is going to be linear. The blue lines indicate extrapolation of that, both at the bottom and at the top end. The limit of detection, as we saw earlier, is going to be 3 times the standard deviation of the blank, which is also related to the same thing as the concentration. So the limit of detection is going to be the Y value of this instrument response. So it's going to be like 3 times the standard deviation of the blank. The CM is going to be the the minimum concentration to be detected. And that's going to be the X value at that point. Now, that's whenever we can start to say that, okay, we have analyte present, but it's not enough to really provide a, how do I say this? To provide a accurate answer. We're going to be saying that more than 50% of the time what we measure is not going to be accurate. Then 10 times the standard deviation of the blank. So there's a significant difference now between the blanks signal and our analyte signal. That is what is called the limit of quantitation, and that is the Y value from which we are able to measure. Any other Y values above that are okay. Any other concentrations above that are okay to be measured. And then we can measure anywhere from there up to the limit of linearity. So usually we're within this range whenever we prepare not only our standard solutions for our calibration curve, but also whenever we want to create or want to measure a sample, it needs an unknown sample. It needs to fall within the boundaries of our standard solutions and definitely within this linear range. So the limit of detection, in other words, is the lowest content that can be measured with reasonable statistical certainty. And the limit of quantitative measurement, the LOQ, is going to be the lowest concentration of an analyte that can be determined with acceptable precision, i.e. repeatability and accuracy under the stated conditions of the test. So the limit of detection is usually 3 times the standard deviation of the noise. And so we can ask ourselves, is this going to be real? So the standard deviation of the noise is going to be this H value. So we have here a peak, which is 1, 2, 3, 4, 5, 6, 7 times the standard deviation of the noise in height, more or less. It's definitely greater than 3 times that H value. And so we can say that this peak is in fact real. So the limit of detection, as we said, is the lowest analyte concentration that can be detected at a known confidence level. And so the signal must be bigger than random noise of the blank. And so usually K is greater than 3. So that means it's going to be 3 times the standard deviation of the blank. So we have the limit of detection is equal to the minimum signal is going to be equal to the mean of the signals of the blank plus Ks blank, where K is this number greater than 3 and S is the standard deviation of the blank. So this usually we would take the, say, seven or more blank recordings and then take the mean value of those and then also create a standard deviation for those values. So how do we go about determining the limit of detection and the limit of quantitation? So usually we would measure the signal of n samples where n is greater than 7. Then we would compute the standard deviation and the mean for these. And then to get the limit of detection, the detection limit, y value, is going to be equal to the sum of, or sorry, the mean of the blank values plus 3 times the standard deviation of the blank. And then the limit of detection can also be expressed as 3 times the standard deviation of the divided by the m value, which is the gradient of the calibration curve. And then for the limit of quantitation, it's going to be 10 times the standard deviation divided by m, where m is going to be the gradient again of the calibration curve. So we take this standard deviation and we can get both the limit of quantitation and the limit of detection. So the sensitivity then of both instrument and method is the ability to distinguish between small differences in analyte concentration. So from this one, we can see what happens is the steeper the gradient of our calibration curve, the more sensitive that method is to a particular analyte. So the sensitivity of an analytical method can be defined as the slope of the calibration curve, that is, as the ratio of change in the instrument response with the change in analyte concentration. So the steeper is going to be equal to better. It's going to be more sensitive. So we've talked a lot about these calibration curves. We've talked about how we can form them using linear regression, but how do we actually use these? So in the linear range, a calibration curve has the equation absorbance is equal to 2 times the mass, where mass is in micrograms, plus 0.004. And what is the mass if an unknown absorbance is 0.402 and a blank absorbance is 0.084? So the reason why we're given the blank absorbance is so that we can get the corrected absorbance. So the corrected absorbance is going to be equal to the 0.402 minus 0.084, which is going to be equal to 0.318. So then we can rearrange this to get absorbance is equal, or rearrange the y is equal to mx plus c curve for our calibration curve, so that we get it in terms of the mass of in micrograms. So that's going to be equal to absorbance minus this C value divided by the gradient is going to be equal to 0.314 divided by 2, which will be equal to 0.157 micrograms for our unknown sample. So that's, we've got in our unknown sample, we have a mass of 0.157 micrograms. So that's how we would use a calibration curve to find an unknown value. So figures of merit accuracy. So this is the ability to get close to the true mean. So determinate errors are usually our biggest problem in calculating these. So determinate errors are also systematic errors, and these can come from various different locations. So common ones are the operator or the method or instrumental. So the accuracy of a particular measurement can also be described as the bias, provides a measure of the systematic or determinate error of an analytical method. And so bias can be calculated as the difference from the mean of the sample and the true mean. So determining bias involves analyzing one or more standard reference materials whose analyte concentration is known. So if we remember back to part 1, we discussed this in terms of the t-test, where we were looking at the sulfur content of a particular coal sample, and we were comparing that to a certified standard material which had a known concentration of sulfur. So for more on that, check part 1. Bias is eliminated or corrected through use of blanks and by instrument calibration. So further on for specificity, so usually we might want to check our method and see if it's reasonable for what we're doing, so that sometimes there are a lot of peaks, like down at the bottom here on the left-hand side and on the right-hand side. So we have here, this is a chromatogram. So we have instrument response on the y-axis and time along on the x-axis. So this is time out of the detector or residence time in the column. So what you can see here is a lot of the peaks overlap with each other. They don't go down to the baseline properly. And so these are not well resolved, as we say. So in this instance, this method is not particularly good for this sample. And so we should modify it so that we get a sample more like this. Now, even though we can see that there is some degree of slant to the baseline, that's okay because we can still draw a straight line here and all of the peaks go down to that baseline. And they're well resolved, meaning that we can find the area exactly for each peak, and it's not complicated by multiple interfering species. Accuracy and precision, then we've already talked a little bit about this. So precision is the ability to reproduce the measurements. That means that even if we produce a large number of replicate measurements, they're all going to be pretty much the same, and the standard deviation is going to be low, meaning the variance is not very high. Now, for accuracy, that's going to be the nearness to the truth. So precision doesn't actually mean that we have an accurate measurement or a close value to the true mean. It just means that we're getting the same result every time. Accuracy means that we're close to the true mean. So we can compare results with more than one analytical technique, and we can analyze a blank spiked with a known amount of analyte to try and check for our precision or accuracy. So think of accuracy, if we think of a darts board where accuracy maybe, if we want to hit the bullseye, would be hitting the bullseye every time. That would be highly precise and highly accurate. High precision could also be hitting the one value every time. That would still be very precise, but our accuracy, if we were aiming for the bullseye, would be very bad. So those are sort of real world examples of precision and accuracy. But these have all been for relatively simple systems. What happens whenever we have a complicated system, like pollution in a river? You can see this river is polluted with bits of wood, and I mean, most of it's natural detritus, so it's not terribly polluted, but some of these things are potentially going to be harmful for the river. And so we want to maybe analyze that and see what effect it's having on our environment. So how do we measure these complicated samples? So oftentimes we have to consider what's actually in the sample. So far we have only considered simple systems. Many environmental systems are complex mixtures of interacting and interfering species. So if we look at this chemical plant, maybe it's a refinery, it is situated by a large body of water. This is often because these plants need a lot of water for cooling processes. So they're often situated near rivers, but their situation point near rivers can often cause potential pollution problems. And so they need to be monitored to make sure that they're not sort of dispensing of their polluted water into the river water. And so how do we analyze these samples? Because the matrix here in this river water doesn't just contain the pollutant in water, it also contains other things like dissolved ions. It can contain other pollutants, maybe from other sources. And so we need to make sure that what we're measuring with our instrument is actually going to be representative of the real world sample. And so there are a number of techniques that we can use to overcome this. So the reason why this is a problem is because of the matrix effect. It's not the movie. The matrix effect is the effect of the components of our sample on the analyte that we're interested in. So the matrix is everything in the sample other than the analyte, and its effect on the response is called the matrix effect. So impurities can interact with the analyte, which may change the instrument response. This causes calibration curves based on pure analyte samples to be unreliable. So we'll see an example of this as we move through. And so standard addition is one of the ways that we can alleviate this. So the standard addition is a method to determine the amount of analyte in an unknown. So known quantities of analyte are added to a sample with unknown concentration, and the analyte concentration can be determined from this increase in signal. So what's happening here is that we have our unknown sample of, for example, river water, and say we want to measure the quantity of dissolved iron 2+ ions there. So we obviously are not quite sure how much iron we have. That's our unknown. That's the analyte we want to know. So what we would do is we would add known quantities of iron to our environmental sample, the river water with iron present. And then we would measure those samples. We would measure the one with no added iron, we would measure the response in the, let's say, 5 ppm added iron, 10 ppm added iron, and so on until we can create a calibration curve. And then based on that calibration curve, we're able to extrapolate back to find the concentration of our iron in the original river water sample. And so we'll see how that process happens. So standard addition is often used when the sample is unknown or complex and when species other than the analyte affect the signal. So this is why we're actually interested in doing the standard addition method, because say we have perchlorate, which is ClO4 minus, and this affects the production of thyroid hormone in humans. And so it can be particularly dangerous if we have a large amount. Now, the problem is that this perchlorate is typically detected by mass spectrometry, but the response to the analyte is affected by other species present in the sample matrix. So for example, here we can see a comparison of the perchlorate calibration curves depending on the solvent used. So if we were to prepare perchlorate in groundwater samples, that's water taken from underground reservoirs or aquifers, then you can see that the response for our instrument to perchlorate is much lower than it would be if we prepared this with distilled water. And this is caused by interfering species, other species in the matrix, which change the response of the instrument to the perchlorate. And so the response of calibration standards here is very different from the real samples. So how do we go about using the standard addition method? So the standard addition formula is here, where we have the initial concentration of the analyte over the concentration of the standard in the final solution plus the concentration of the analyte in the final concentration. Now remember, because we're adding known amounts of standards and diluting to common volumes, we will actually change the concentration of the analyte as well. The analyte will get more dilute. And so that's going to be equal to the initial response the response to the analyte over the response to the analyte plus the standard. And so we can rearrange this to be in terms of the final concentration of the analyte is equal to the initial concentration of the analyte times the dilution factor, and the standard, or the final concentration of the standard, is going to be equal to the initial concentration of the standard before it's added to the mixture, over the dilution factor for that. And so expression of the diluted analyte concentration in terms of the original concentration allows the problem to be solved as the other terms are also known. So let's see an example of how that's done graphically. So here we have 5 flasks, each filled with 5 milliliters of our own unknown sample. So say this could be our river water. Say we collected 500 milliliters of river water, and we would place 5 milliliters in each one of these 25 or 50 milliliter volumetric flasks. So you can see they have a marking here, which is to their 50 milliliter volume. And so if you want to know more about volumetric flasks, check in a previous part of this course. So we can then add a certain amount of standards. So we'll add, in the first one, we won't add any standards. So we just have the dilute unknown in this case, then the response of the dilute unknown. Then we have the concentration, or we got the dilute unknown plus some of the standard 5 millimeters of standard, 10, 15, 20, and so on. And then we dilute this further up to the 50 milliliter mark so that each one has the same volume. And then we take a sample from each one of those and measure it using our instrument, which will allow us to form this graph of response, instrument response versus concentration of added analyte. And so that's going to be similar to the concentration of the standard. So here we have different points. We have here at 0, the unknown without standard. So this had, remember, 0 milliliters of standard added. Then we have 5 milliliters, which corresponds to 0.04 moles per liter. Here we added 10 milliliters, which was 0.08 moles per liter, and so on. And so these can be used. We can form via linear regression our calibration curve. And then by extrapolation, we can go back to find the final concentration of the unknown. So an internal standard is another way about going about this, different from the standard addition method. And so in this case, we add a known amount of a standard to our unknown sample. And so this is only really possible whenever we know how the instrument will respond to our analyte and how it will also respond to our internal standard. But we can determine that. So internal standards are used when the detector response varies slightly from run to run because of hard to control parameters, such as flow rate in a chromatograph. So that means that since, say, for example, we added 5 ppm of a standard to our unknown sample every single time, then we could find the peak area for that standard, and then we could correct our unknown sample so that we would always have the corrected response. So the response factor, so say this is what a chromatogram with a standard added and the response of our unknown in them would look like. So we would have two peaks, one for the, this is the injection point, one for the unknown and one for the standard that's added. So the detector usually has a different response for each species. So the response factor F for the analyte needs to be determined. To determine the response factor, a known amount of analyte and standard are mixed and measured. So we have here the absorbance of the analyte over the concentration of the analyte is equal to the response factor times the absorbance of the standard over the concentration of the standard, where X and S are the concentrations of analyte and standard after mixing. So how do we then calculate an example of this? So say we had a mixture of sodium and potassium ions with these known concentrations. We measure them and we get chromatographic peaks of these two values respectively. To analyze the unknown, so the reason why we're given this is so that we can work out the response factor. So we have the concentrations of both sodium and potassium, and we have the absorbances of both sodium and potassium. So now we can find F, because F is the only thing we don't know in that equation. Then we're asked to analyze an unknown using this information. So 10.0 milliliters of 0.146 molar K plus was added to 10 milliliters of unknown before being diluted to 25 milliliters. The peaks measured 553 and 582 atomic arbitrary units. What is the concentration of sodium in the unknown? So first find the response factor F. So this is using this equation that we had just a moment ago. So the only thing we don't know here is the F value. We know the absorbance, it's here. We know the concentration, it's here. We know the absorbance of K, it's here. And we know the the absorbance of K is here. And we know the concentration of K, which is here. So we then fill in those values or rearrange so that it's in terms of F. So we divide through by this term. And so we get F, and then that's going to be equal to fill in the values. And so that's then going to be equal to 0.970 as the response factor. So now that we have the F, we can continue to look and see what is the K plus in the mixture of unknown and standard. So K plus is going to be equal to the concentration here times the concentration added over the final volume. And so then take F, the K plus standard, and the information from the question to find the Na plus concentration in the mixture. So we then fill in our values. This time we know everything except the sodium ion concentration, which is what we want to know. So we then fill in all those values into our equation, and we get the Na plus concentration as being 0.0572 moles per liter. And so now we just need to, in order to find the Na plus concentration in the unknown, we just need to go via our dilution factor. So Na plus in unknown was diluted in the mixture by K plus and also by the extra water. And so the Na plus concentration in the unknown was then this. So we have to multiply by this dilution factor. So 25 milliliters in the original volume over the 10 milliliters from the sample is going to be equal to 0.143 molar as our concentration in the unknown sample. So that's how you would use the internal standard method to determine the concentration of an unknown. So in summary, then, we've gone through all of the different types of calibration methods. We've gone through method development. We've gone through different statistical tests for our analytical and instrumental measurements. And so quantitative or instrumental analysis is based on the signal to concentration relationship. That measured instrument response is going to be proportional to the analyte concentration. So the signal is going to be proportional to concentration, or signal is going to be equal to mx plus the signal of the blank. So the concentration then is going to be equal to the signal minus the signal of the blank over m, which is the gradient. And so common calibration methods are the use of calibration curves. We have the standard addition method, and we have the internal standard method. So the calibration curves is the general simplest way of doing it. The standard addition method is when we're dealing with complicated samples, such as environmental samples. And then the internal standard method is whenever we have differing instrument responses between runs. So that brings us on to our comprehension check. So I'll read out the question as always, and then give you some time to work through it. Make sure to pause if you need more time. And so the question is, in the linear range, a calibration curve has the equation absorbance is equal to 1.2 times the concentration in moles per liter plus 0.013. And we're asked, what is the mass if an unknown substance absorbance is 0.457 and a blank absorbance is 0.143? Okay, pause for more time if you need it. Okay, we're going to go through the answer soon. Please pause if you need more time. So the corrected absorbance then is going to be 0.457 minus 0.143, which gives us the corrected absorbance as 0.314. We can then rearrange the equation as we did earlier to be in terms of the X value or the concentration. So that's then going to be equal to the corrected absorbance minus the C value over the gradient, which is going to be equal to 0.301 over 2, which will give us a value, or 1.2, which will give us a value of 0.25. Okay, that brings us to the end of part 2 of statistics and chemical measurements. Thank you for watching.